Kim. Did we get any myths in the inbox this morning?
We sure do, JT. Let's take a look. So we have a customer that wants to know if core shell columns are actually really better and provide more efficiency than fully porous columns.
Yeah, that's great. I see that. Solid core, core shell, superficially porous, they're all the same thing. And over the past 5 to 10 years, customers have really seen a benefit, supposedly in efficiency, for these types of particles.
Yep, you're right. I see a lot of customers talking about them and asking for them because they believe that they're going to get a real benefit in resolution, right, in the run due to the increased efficiency.
Yeah, I think this is something we definitely should take a look at. But first, let's take a step back and just give our audience like a background as to what these particles look like.
That's a good idea.
So Kim, here's a couple images of some superficially porous particles. The cartoon image on the left is what you see typically in the marketing brochures. And as you look at this, you can see that it's a solid core or a solid mass surrounded by a superficially porous shell. The image to the right is an actual particle that we cut in half with a focused ion beam. And again, this image really depicts what a solid core particle is. So again, the solid core surrounded by that superficially porous shell where all the chromatography takes place.
That's really interesting, JT. You know, I've never really looked at a cross-section of one of these particles before. But how do you think we can fairly assess the differences in performance between a fully porous column and a core shell column?
Yeah, great question, Kim. I think for this myth, we're going to have to run some Van Diemter curves, and I'll talk about those now.
Van Diemter, okay.
So Kim, the Van Diemter equation describes empirically additive sources of dispersion that result as a function of the mobile phase velocity and the particle size. And you can see that in the equation shown on the screen. From the equation, you'll see the three terms, the A term, the B term, and the C term. And each one is additive to the overall band spreading or efficiency of that material. So if we think about the A term, that takes into account the flow heterogeneity. And it's a constant with the particle size of the material. The B term is the longitudinal diffusion, which diminishes as you increase the velocity. The C term, or the mass transfer, increases with the linear velocity and is directly proportional to the particle size squared.
Very interesting, JT. I think we should actually use the reduced version of the Van Diemter equation because the reduced version allows us to compare columns that have different particle size running different probes. This way it's kind of unitless, right? We can also do some independent measurements of each of these terms and see if there are any differences between the solid core and the fully porous particles.
So Kim, it just happens that I actually have a couple columns right here on my bench that we can run.
All right.
So I got here a solid core column, so a cortex column, and a fully porous acuity column, 1.6 micron and 1.7 micron.
Excellent.
So I figure we can run the Van Diemter curves on our system and then look at the results.
All right, let's get going.
All right, let's do it. So Kim, these curves look really good. As you can see on the top, we have our solid core cortex column that we ran, and then below it we ran our fully porous acuity BEHC18 column. And as you look at the reduced plate height, or the H minimum, you can see that for the cortex or the solid core column, it's 1.6. And for the fully porous, it's 1.9. And having a lower H minimum, or reduced plate height, means it's more efficient.
And when we look at the individual contributions from the A, B, and C terms, we can actually see it's the reduction in the B term. So in the cortex C18 column, the B term is 4.2. In the fully porous column, the B term is 6.9. So it's that reduction in B term, the longitudinal diffusion, that's significantly contributing to the greater performance.
So Kim, how do you want to call this myth? I mean, based on the original question, do solid core columns provide more efficiency when compared to their fully porous packed columns?
Yep, so this one is absolutely trusted. I think from the Van Diemter curves we saw that they really do, with that decrease in longitudinal diffusion, they provide more efficiency than the fully porous columns.
Yeah, this myth is trusted.
Yep, you want to write it up or I will?
Go ahead.
Okay. If you'd like your question to be answered on a future episode, please feel free to email us at trustyourscience@waters.com.